I'm recording this. Yep. So here we are going to find if you are sometimes you are getting polar coordinates, you are getting curves expressed in polar coordinates. So how do you find the length of that in that time? Yep. So here look at this. So this is a polar coordinate. So this curve expressed in polar coordinate. Then if you are not in x and y, right? So how do you find the length of this curve, your parameter curve? So let's consider two-dimensional space and consider any general point in this plane. Yeah, x is the corresponding x coordinate and y coordinate, and you can express x and y in terms of this r and theta. How do you do that? Yeah, so are not included in PDF. Yeah, I will upload this. Yeah. So how do you express x in terms of r and theta? X, y. Yep. Yep. X is equal to what? Yep. X, because this is a rectangle. Yep. X is r cosine theta. Yeah. X coordinate r cosine theta. Y r sine of theta. So then you can express this P in terms of these two parameter values, R and theta. And this is the relationship between rectangular or Cartesian coordinate and polar coordinates. And here R would be take 0, and it is a non-negative value, right? And theta in between 0 and 2 pi. So if you have parameter r and theta in this behaves in this way, r is a non-negative number and theta is a angle. Some people take minus pi to pi. Yeah, that's my you can take if you like. Yeah, some people consider theta varies between minus pi to pi. That's all right. Here to there. Yeah, that's okay. That's fine. Or you can use 0 to 2 pi. Yeah, full circle. Right. So x and y can be expressed in terms of r and theta like this. Then you can find, so x is a function of t, then r and theta is function of t. Yeah, you can find these derivatives dx by d theta. R is a function, depends on theta, yep. So here like this here, R is equal to this, yep. So then you can find dx by d theta, similar dy by d theta, and here, so and finally you can show that the length of that polar curve, is given by square root of this one squared plus this. Yeah. So if you are given polar equation this way, you have to apply this one here. Okay, go to this. So this is very important. So now I will change the variable. So our our position vector, right, or position vector of a particle, if you consider a practical physics problem, right, you throw a ball, so you know the position vector of the ball at a given time t, right, it is given. So now I'm going to express the position vector in terms of this arc length. How do you do that? Yep. Please upload this. Yep. After this, I will upload definitely. Yep. Yeah, so how do you express this position vector of a particle in terms of arc length? S is the arc variable, arc length as a parameter. So you write this position vector in terms of arc length. How do you do that? Yeah, let's do that. So all the time, remember, yeah, all the time we are getting the position vector or position in terms of t variable. Now we are going to change this t to s. S is the arc length. Okay. So how do you do that? Okay. So for that, you have to consider a particular space curve, right? So you know the equation. Yeah, this is C is given by this equation. Yeah. Yeah, C is given by this equation. Yeah, like this. Remember, yeah. This is your C. So this is your helix, famous helix. C is this one. It is expressed in terms of the single parameter t. Now I will convert this C or this one in terms of S. S is the arc length. Okay, let's see. Okay, now you have the equation in terms of T. Yeah. Uh-huh. So now you have to choose a reference point. Okay. Pick a reference point. Yeah, I will pick this point as my reference point, right? T naught. So start from the reference point. Yeah, T naught is my reference point. Yeah. Okay. So this is my, yeah, so like, yeah, reference point. Fix, it is fixed. You have to, yeah, pick that. Okay. Now I will increase, if you increase your parameter from T naught to above. So this, before that, let me explain. Yeah, first pick this reference point in this parameter T, right? Yeah, this is your reference. Okay. And the corresponding curve point on the curve is this one here, R of T naught. And this is your reference point. Okay. Yeah, this is your reference point. Yes. Yeah. Reference point. Okay. Moving along this curve in this direction. Okay, I'm moving along this curve in this direction. Then I increase this to do that. You increase this parameter value from T naught to here, T naught to these values. One of the, yep. Let's say T1. Yeah. You increase T variable from T to T1, then this point is moving slowly from S naught, yeah, from this point to, let's say, yeah, from this point to this point. Then you can find, yeah. So if you, yeah, so then you can find this length, right? Using previous equation, you can find this length. Right. In generally, let's assume, yeah, you change the parameter value from T naught to, let's say, T general point. Then from this reference point, this point is moving along this path up to some general point, yeah, here, and this length would be your S. This is your S. All right. So now I will express this R in terms of this variable. S. If so, this S is positive. Here, look at this. P So this is your P. Yeah, P is on the curve. Yeah, this is your P. If the P is on the curve, let us be the sign. Right? Yeah. So yeah. So this is positive S, and if this T, yeah, lies below this T naught, let's say, yeah, so lies here. So if this is your T, then yeah, this is your minus T, let's say minus TOT. Then you can say, and the corresponding arc length is negative. P is in the negative. Oh, give me a second, right? Give me a second. Oh, yeah, so this case is a special case, right? So the corresponding parameter value is 0, right? Corresponding parameter value is 0. So this is my reference point, and the corresponding parameter value is 0, and I choose a general point. If I vary my parameter to this general T, then my arc, so then I get this, I get the length of this arc, and this is the corresponding points. Yeah, for this one, and this is the corresponding parameter value, right? And I could express this helix equation in terms of this arc length because of this relationship. Okay. Okay. Now I want to talk about. I want to make this more general, right? So if I, yeah, so that's why, yeah, I'm going to do, right, wait a second, yeah, here, you can see that, yep. Before that, let's discuss a couple of examples. So let me apply this chain rule, right? So you know that our R expressed in terms of T, right? So I want to express this R in terms of a different variable, let's say tau, right? Tau is a different variable. Tau is a function of t. Let's say you could find the function of tau, right? So you know the relationship between tau and t. If you know the relationship between tau and t, you can express this R in terms of tau very easily. If you know the relation, let's say before, yeah, this is the relationship between t and s, then you can express this curve in terms of s, yep, like this, yep. Right, in generally, yeah, so first I have this curve, yeah, this base curve. I'm going to express this one in terms of tau, yep. So for that I use chain rule, yep. So you can use chain rule definitely here. So what is this? What is this one? This is the magnitude of dr du, right? So you have to find this. You have to find, yeah, you have to find dr d tau, right? Yeah, so, right. So, but my equation, everything in terms of t, because of that. So if you know this relation here, yes, this relation, let's say tau is equal square root of 2 over t. If you know this kind of relation, so I'm able to express this in terms of tau by using chain rule here. So yeah, let's use chain rule. Yeah, dr by d tau is this one. This is the definition, right? Now you have to differentiate corresponding components with respect to tau. Now, yeah, you can use chain rule. Dx d tau is same with Yeah, so in A levels also, yeah, dt, yeah, d tau, yeah. So yeah, so I use chain rule here. I apply chain rule. So you know this one here, yeah. So this guy is common for all components. You can, yeah, can take it out from this vector. Yeah, take it out because it is a scalar. Here, this is not a vector. You can take it out from the vector. Yep. So then you left with dx by dt, dy by dt, dz by dt times this scalar. Yeah, if you know this conversion, you can find this very easily. Yeah, then dr vector r by d tau is equal to dr. This is chain rule basically. Yep, this is chain rule. If you have a vector function and different variable is equal to, you can apply chain rule for vector functions. Yeah. Now, right, if you consider magnitude and magnitude of these things, yeah, product of magnitudes. Yeah, so you need magnitude here. This is the magnitude. That means the magnitude of is each component, magnitude of this scalar and magnitude of this vector. Got it? All right. So then you integrate this. Yep, integrate. Where's that? Integrate from the reference point to the general point. Reference point to the general point. Got it? Then you get S, general arc length S. Magnitude, magnitude of, yeah, dr vector function dr by that transformed variable. Yeah, from reference to gender. Got it? Yeah, so that is right. So this is the example. This example gives you that conversion is correct. Yeah, this one is correct. So you can apply chain rule for vector value function. So this is the chain rule basically. So chain rule for vector value function, vector valued function. Right. Got it? So in this, in this example, shows you this relationship is this relationship serves. Yeah. So here, look at this. R expressed in t variable, and so this is your famous helix curve expressed in t variable, and for helix you found this relation S is equal to T square root 2. Yep. So you know that you know that conversion. Because of that, you could express R in terms of S. Right. So let's see whether this equality is true. Right. Okay. Let's find dr by dt, which is square root 2. Yeah, this is square root 2. Yeah, this is square root 2. What happened to, so what is dt? So do you know the, s, t is equal to, this is the conversion, s over square root 2. You found that dr over dt is equal to square root 2, and let's find dt over ds. dt over ds is 1 over square root 2. When you multiply these two, you get 1. 1. Let's see whether, let's find dr by ds. So when you find that, so you have r in terms of s, you can find dr, magnitude of dr by ds, right? Very easy, because you have this one expressed in terms of s. So all you need to do is differentiate this with respect to s and take the magnitude. So when you do that, you get again one. Yeah, this one is true. Yeah. So you can apply chain rule for vector value function. Got it? Change of parameter. That's the thing. Okay. Before let me